Okay, welcome to this video on combinations, a technique used for counting event space and sample space when considering probability. So first of all, there is two distinct trains of thought here. Either we're dealing with questions that involve order, and if we are, then we use permutations from a previous lesson. Or we're considering questions and scenarios that has no importance on order. And in that case, we consider the technique of combinations. Okay, let's look at the notation. In standard notation, permutations can be written as P bracket N choose R or N choose R permutations. And for combinations, those notations are similar, C bracket N choose R or N choose R combinations. And there's an additional notation where it's N R inside large brackets. So this third notation as a way to write combinations. Okay, now what do they translate to in terms of calculations? On the permutation side, it's n factorial divided by n minus r factorial. On the combination side, you see that similar calculation in the exact same position, n factorial over n minus r factorial, and there's an additional division here of r factorial. What is that? That is the number of identical selections that, if order was important, would be counted. But since order is not important, you divide that out to reduce the count, because we're talking about selections versus arrangements. Another way to think of permutations is an arrangement. So AB is different than BA. But on the combination side, you're thinking of selections where AB, that's the same as BA. So where AB and BA would lead to a count of 2, on the combination side or selection side, that leads to a count of 1 because they're the same selection. Whether you have AB in your hand or you have BA in your hand, you have the same letters in your hand. So it's a count of 1 in terms of the selections. So if you were to take 2 and divide it by 2 factorial, you're going to end up with 1. And that's the divided by r factorial. That takes care of the identical selections. Okay, let's consider this first example. It asks you to arrange 5 cards from the hearts from the deck of cards. So there's 13 hearts in the deck, and you have to arrange 5 of them. So for example, we could have the 2, 7, Jack, Queen, King, or we could reverse the 7, the 2 and the 7, and now we have a different arrangement, which is 7, 2, Jack, Queen, King. Or we can move the Jack around, and we have Jack, 2, 7, Queen, King, etc. So there's going to be 5 factorial ways to rearrange the same selection. Keep that in mind. There's 5 factorial ways, 5 choices for the first position, followed by 4 choices, followed by 3, followed by 2, followed by 1. That's 5 factorial ways to rearrange this selection. But because it's an arrangement, because the example is asking for an arrangement, those are different ways. And using the permutation calculation, we end up with 154,440 ways to select 5 hearts from the 13 available hearts. And then the calculation looks like 13 factorial over 13 minus 5 factorial, which reduces the 13 factorial over 8 factorial, which equals that count of 154,440. Now, if we take this same scenario where 5 cards are being taken from the 13 cards, but not an arrangement, just a selection. So if we're going to select 5 hearts, the quick calculation is 13 choose 5 combinations, because order is not important anymore. But let's dive into this a little deeper. Let's take the permutation calculation of 13 permutation 5, and let's recognize that 5 factorial ways for these selections to be rearranged is included in the permutation count. But because those 5 factorial ways are the same selection, we could divide that out. So if we divide out the 5 factorial, 154,440 divided by 5 factorial, that'll equal 1,287. And that's the same answer if we use the combination formula. So let's understand why it's the same. Well, the permutation portion is 13 factorial over 8 factorial. Recall from our previous work up top here. And if we add the division of the 5 factorial, so we add this division, it equals 1,287 selections. And if we go backwards, that is what the combination formula would have given us as well. 13 factorial over 13 minus 5 factorial, also divided by 5 factorial, which is 13 factorial over 8 factorial times 5 factorial. So you could see the permutation portion as well as the combination portion that equals the same answer of 1,287 ways to select 1,287 ways to select 5 hearts from the 13 hearts available in the deck. And thus the combination formula is more efficient because it'll go straight to that calculation, and you don't need to consider that you're dividing out identical selections, sorry. Okay, let's consider this example and how combinations can help us. A co-ed volleyball team consists of 5 males and 5 females. 15 males try out for the team and 18 females try out the team. How many ways can the team be selected? Well, so it's not important how they were selected. It's not important the order of the selection. It's just important that they were selected. So whether a person was selected first or second doesn't change the count. What matters is that they were selected for the team, that they're on the team. So this example is a non-order example. Therefore, use combinations to count efficiently. So we have 15 males trying out, and we need to select 5. So that's 15 combination 5. And so we're going to use the multiplicative principle. There's 18 females trying out for the team, and 5 are going to be selected. So when we work out each combination, and we remember it's a compound event, so we're using the multiplicative principle, fundamental counting principles, we come up with an event space of 25,729,704 ways that this is possible. Now, why is this event space? Because there's a restriction that we need 5 males and 5 females. So let's think probability for a second. What would the sample space be? Well, there's 15 males and 18 females trying out, so there's a total of 33 players trying out. Yes, it needs to be a co-ed team. Yes, it needs to be 5 males, 5 females. But in general, 10 are being selected. So if you remove the restrictions, there's 33. And we're selecting 10, and order's not important, so we're using combinations. So the sample space becomes 92 million ways, approximately 92,561,040 ways that this can happen. So what's the probability that this could happen? What's the probability that a co-ed volleyball team with 18 females and 15 males trying out can have 5 males and 5 females? Well, we put our event space our event space over our sample space, and we have the probability that that can occur. So 25 million approximately over 92 million approximately is the probability that this can occur. So as a combination, that would look like 15, I'll write it in the other format. 15 males, select 5, times 18 females, select 5, over 33 players in general, select 10. So I'll write it as a combination there, and that ends up equaling this fraction above. Okay, in this final example, we're asked how many lines can be drawn. And if you look at the arrangement of points, and you consider point A and point B alone for a moment, why am I considering point A and B alone? Because to draw a line, you need 2 points. That's it. You just need 2 points. So if we take A and B, whether I connect A to B or I connect B to A, that's the same line. So non-order. So maybe we could use combinations. And the answer is yes, that'll be more efficient. So first you need to consider how many points form a line. Then you need to consider that the order is not important. And then you need to count how many points there are here, and there's 9 points. So we're starting with 9 points, and we only need to select 2 to form a line. So the efficient calculation would be 9 choose 2 combination, which equals 36. So therefore, 36 lines can be drawn given the original setup of the points as you can see in the diagram here, the original setup of the points. So based on these 9 points, and we're selecting 2 at any given time to draw a line, there's 36 ways that can occur. And that concludes this video on combinations, the difference between combinations and permutations, where order is not important. The selection's important, not the arrangement of the selection. And thank you for watching the video. Please subscribe to the channel so you can be alerted to more videos. Hopefully you found this meaningful and helpful. And you guys are awesome. Have a great day.